The last chapter, chapter 6, that we're going to look at is about Laplace transforms. And here's the definition of Laplace transforms. It isn't obvious at all why this is going to help us solve differential equations, but hang on. So this is a transform because it takes a function of t, y of t, integrates over t times e to the minus st, where s is a constant as far as the integration is concerned. So this just gives you a constant, but the constant depends on s. So it basically gives you a function of s, because for each different s, this gives a different integral. So it transforms a function, a given function, little y of t, into what we'll usually call capital Y will be the Laplace transform. On page 626 of your book, there's a list of the Laplace transforms of a bunch of basic functions. For example, e to the at, where a is a constant, the transform is 1 over s minus a. And there's several others here that we'll look at later. This page is very important. I'll always give it to you on tests. I always give a photocopy of this, or at least give the formulas they need, because you don't need to remember all these. We're only going to drive a couple of them. But you'll need to refer to it because the table is very important in taking Laplace transforms. So e to the at, the transform is 1 over s minus a. And here's the most important formula that we're also going to look at. This is what helps us to solve differential equations, is the Laplace transform of y prime is s times the Laplace transform of y minus y of 0. So it basically gets rid of the derivative for us here. So this formula is key. Well, in that table on page 626, as we just pointed out, one of the entries is the Laplace transform of e to the at is 1 over s minus a. Let's derive that one since that's important. The Laplace transform of any function is the integral of that function times e to the minus st. So that's e to the a minus st, and that's pretty easy to integrate that. Remember, s is just a constant. And so is a, so that's just e to the a minus st. So integral of e to the constant t is just 1 over the constant times e to the constant t. That a and s are both constants. T is the variable. And you plug in the upper limit of infinity. Basically, they take the limit here, but let's just say e to the minus a minus s infinity, at least when s is bigger than a. That's going to be 0, so the upper limit 0, the lower limit t is 0, so you just get 1 over a minus s, minus 1 over a minus s, so it's 1 over s minus a. So we've actually derived one of the formulas. There's a bunch of others, the Laplace transform of sine of omega t and polynomials and so forth, and they're just a question of using the definition and doing the integration. For example, if you want the Laplace transform of sine of omega t, you just integrate sine of omega t e to the minus st, where omega and s are constants, and that is not real easy to integrate, but you can do a couple integration by parts and get it, and you get that formula, and it's in the tables, and there's no need for you to derive that every time you use it. Just look it up in the table, and there's Laplace transforms of e to the at, sine of omega t, and things like that. So we'll just rely on that table. But as I said, the formula in that table that's most important, that helps us to solve differential equations, is the one that says the Laplace transform of y prime is s times the Laplace transform of y minus y of 0. And you prove that, well, just if you want the transform of any function, dy dt, you put it in there times e to the minus st and integrate it. And you basically have to do an integration by parts, integrate the y prime and differentiate that. And you end up with 0 minus y of 0 times e to the 0, which is 1. So minus y of 0 here, and this is just the, well, you take the s out. So remember, s is a constant, t is the variable in this integral. So take the s out, and you have s times what's left is just the Laplace transform of y. So just one integration by parts to prove this formula, and it's key to solving differential equations. It gets rid of the derivative. So the Laplace transform basically solves constant coefficient non-homogeneous linear equation. So these have to be constant coefficient. It's non-homogeneous. F of t doesn't have to be a constant. And you'll notice we already know how to solve problems of this form, at least if f is a exponential, sine or cosine, or a polynomial, but we didn't learn how to solve any others. Well, Laplace transform still requires constant coefficients here and has to be linear, but it'll allow us to solve problems with more general, more complicated f of t's, in particular discontinuous functions and spike functions, delta functions. So it's apparently important in electrical engineering. Circuits can be modeled by equations like this, where the f can be a discontinuous function and so forth. So anyway, it looks like today it's going to look like we won't be able to solve anything except equations that we already knew how to solve, but the next video will handle more general f's. So here's the three formulas that are most important. The others you just look on that table, but the Laplace transform of a derivative is s times Laplace transform y minus y of 0. We showed that, how that can be verified using integration by parts. Now the table didn't actually give this formula. This is very important. I usually write it out on that table because you use it every time you solve a second order differential equation. And that is the Laplace transform of the second derivative is s squared Laplace transform of y minus s y of 0 minus y prime of 0. And I guess the reason they don't have that formula on the tables is you can derive it directly from this, but it's still, you're going to use it so much, you just need to memorize it or write it down on that table, because, you know, the Laplace transform y double prime is just s times the Laplace transform of y prime minus y prime of 0. So just apply this formula to y prime, and then apply this formula to L of y prime again, s L of y minus y of 0. So basically just apply this formula twice. You don't have to do the integration by parts again or anything. And you get s squared Laplace transform of y minus s y of 0 minus y prime of 0. So this formula is for the Laplace transform of y double prime. This is for Laplace transform of y. And this one we use so often. Laplace transform of constant times t is 1 over s minus that constant. So these three formulas you probably need to know by heart. The others you can look up on the table. Well, you can look these up on the table too, but it'll slow you down a little. Okay, so how in the world does this help us to solve differential equations? Well, let's take a simple first order equation to show you how. Okay, here's a real simple first order linear equation with initial condition. We certainly know how to solve that from way back in chapter 1. General solution would be c e to the minus t, 4t, and then you plug in t equals 0, y equals 3, and get c equals 3. So you could skip right down. You can actually solve it easier in chapter 1 than what we're going to do now. But nevertheless, let's use Laplace transforms. Okay. Well, first of all, Laplace transform is linear. That is, Laplace transform of 4y is just 4 times the Laplace transform of y. So we take the Laplace transform of both sides here. And the Laplace transform of 4y is just 4 Laplace transform of y. Because, remember, Laplace transform is just an integral, and constants come out of integrals. And furthermore, the Laplace transform of a sum is the sum of the Laplace transforms, again, because it's an integral, so you can just break an integral up. So integrals are linear, therefore Laplace transforms are also. So you take the Laplace transform of both sides, and that'll be the Laplace transform of y prime plus 4 times the Laplace transform of y equals Laplace transform of 0, which of course is 0 because integral of 0 times e to the minus st is, they don't even have that one on the table because that's so obvious. So now you use the key formula that says the Laplace transform of y prime is s Laplace transform of y minus y of 0, and the derivative's gone, so we don't have a differential equation anymore. We just got an algebraic equation for the Laplace transform of y. Y of 0 is given as 3. Take the 3 on the other side, s plus 4 Laplace transform of y. Therefore, Laplace transform of y is 3 over s plus 4. And you'll always be able to get this far for first or second order linear differential equations. You'll always be able to get to the point where you say the Laplace transform of y is something, because it's just linear. You can easily solve for L of y. That part's easy. The hard part then is to find the inverse transform. That is, now that we know the Laplace transform of y is 3 over s plus 4, what's y? Well, again, you use the linearity and you look up in that table and you say, well, the Laplace transform of e to the minus 4, e to the at is 1 over s minus a. So this is just 1 over s minus a minus 4. So take the 3 out front, and inverse transform of 1 over s plus 4. That's 1 over s minus a minus 4. So it's just e to the at, where a is minus 4. So that one's pretty straightforward. You can just look that up directly in the table and use the table backwards. Let's look at that table again a second. So you'll typically just take the Laplace transform of both sides of your differential equation. On the left, you'll just use the formula for Laplace transform of y prime and the formula for the Laplace transform of y double prime, which we gave you. And then on the right-hand side, well, in our example, the right-hand side was 0, so the Laplace transform was 0, 0. If it had been sine of 3t, we'd look that up here, and here's the Laplace transform of that. But now the hard part is, once you get to Laplace transform of y equals something, is to find the y. In other words, use the table backwards. Well, in our case, we just had 3 over s plus 4. Take the 3 out, and you have a 1 over s minus a minus 4, and so you just use this backwards and say, well, that's inverse transform of 1 over s plus 4 is e to the minus 4t. So that one was pretty straightforward. It's a lot like doing integrals. You know, using integral tables, you look for something that's close to the form you have, and you know, read it backwards. If you have a list of derivatives, you basically use the derivatives backwards for integrals, and the Laplace transform, you use it backwards for the inverse transforms. The inverse transform is the hard part. So you'll always be able to get to here, and then you have to use the table to figure out what function has that as a Laplace transform. And that was pretty easy in this case. And by the way, what if you want the general solution of this problem? This Laplace transforms give you the particular solution that satisfies the given initial conditions. What if you want the general solution? Well, that's simple enough. You just let y of 0 be a, and you'll get a e to the minus 4t. So you can get the general solution just by giving general, you know, letter values for the initial conditions, but it'll give you the exact particular solution that satisfies the initial conditions. So this is a real simple first order equation. Let's look at a little harder second order equation. Okay, so here's a second order equation, y double prime minus 4y equals 12, and with the two initial conditions, y of 0 and y prime of 0 given. You, as always, take the Laplace transform on both sides. And by the way, what's the Laplace transform of a constant? Well, a constant is e to the 0t, and we know the Laplace transform of e to the 0t is 1 over s minus 0. When a is, that's just a special case of a equals 0. So Laplace transform of 1 is 1 over s. So the Laplace transform of 12 is 12 over s. And the Laplace transform, you know, it's linear, so you can break them up term by term. And you got minus 4 Laplace transform of y. And now you use the formula for the Laplace transform of y double prime and you're going to use this formula every time you solve a second order equation. S double prime Laplace transform of y minus s y of 0 minus s prime minus y prime of 0 minus 4 Laplace transform of y equals 12 over s. You want to solve this for Laplace transform of y. So that's s squared minus 4. Put these two together times Laplace transform of y. Take these on the other side. Well, you have the 12 over s. Then you have a plus s times y of 0, which is 2, plus y prime of 0, which is 5. So then you divide by s squared plus 4. and you've got Laplace transform y equals 12 over s. Well, we factor the s squared minus 4 as s minus 2 times s plus 2 for reasons we'll see in a second. So we have 12 over s times s minus 2, s plus 2. Then I have the other term, 2s plus 5 over s minus 2, s plus 2. And now comes the hard part. So we can always get this far. Laplace transform y equals something. How do I do the Laplace transform of, inverse transform of that? Well, if you look at the table, you won't find anything like this. You'll have, inverse transform of 1 over s minus a is e to the at, but you won't find anything with the product of 3 linear functions in the denominator. So what you have to do is partial fractions. You're going to use partial fractions a lot. Remember, when you did integrals, in partial fractions was useful because you couldn't integrate a product, but you can integrate a sum. So you could break this product into the sum of, break this up into something over s plus something over s minus 2 plus something over s plus 2. And then you can find the Laplace transform of these, because that's just, each one of those is 1 over s minus a being 0 here, 2 minus 2. So if we could break this up into a sum of 3 things like this, then we're in business. Same thing here. So you've done this partial fractions before. I'm sure you didn't enjoy it, but when you did integrals, you'd had to break this up into d over s minus 2 plus e over s plus 2 for the same reason that you have to for Laplace transforms, because we can do the transform of these, but we can't do the transform of these products. So we're going to be doing partial fractions a lot. So how do you write this as something over s plus something over s minus 2 plus something over s plus 2? And let's go down to the bottom here where we do that. This should be familiar. Maybe you remember it from doing integrals. So we're trying to find constants a, b, and c such that this is equal to that. Notice this is basically going backwards and finding a common denominator. If I gave you that with constants a, b, and c, you get a common denominator of the product of all 3, and you combine it to do this. So we're kind of finding a common denominator backwards, trying to find the original form. So how do you find a, b, and c? Well, you remember you multiply by the whole denominator here, s minus 2, s plus 2, and multiply this side by the same thing. That just leaves this as a 12. And here the s's cancel and it leaves s minus 2, s plus 2. Here the s minus 2's cancel and leaves the s plus 2. Here the s plus 2's cancel and you leaves the s and s minus 2. And at this point you could multiply all this out and set the coefficient of s squared on the right hand side equal to 0, which is the coefficient of s squared here. Set the coefficient of s equal to 0 and the constant equal to 12, and you get 3 equations for 3 unknowns. But you may recall there's an easier way of doing it. You say, well, this has got to be true for all s, so let's plug in s equals 0, and 2 of the terms disappear, and you get 0 minus 2 times 0 plus 2 times a, so that's minus 4a equals 12. So a is minus 3. That's where we got that from. Then you plug in s equal to 2, and these first and last terms disappear, and you get b times 2 times 4, so 8b equals 12. So b is 12 over 8, 3 halves. Then you plug in s equals minus 2, and these 2 terms disappear, and you get minus 4 times minus 2, that's 8, times c equals 12. So c is 12 over 8, or 3 halves. And that takes care of breaking this up into those 3 terms. Now you break this into these 2 terms. Similarly, multiply both sides by the denominator. That leaves a 2s plus 5 here. And the s minus 2's cancel, leaves s plus 2. S plus 2's cancel here, leaves s minus 2. And again, you could write this out and get 2 equations for d and e, but it's a lot easier to just plug in s equal to 2. And you get 4d equals 2 times 2 plus 5 is 9, so 9 fourths, d is 9 fourths. Plug in s equals minus 2, you get 0, that term disappears, and you get minus 4, e equals, that'll be minus 4 plus 5 is 1, so e is minus 1 fourth. So we've now done the hard part, which is the partial fractions. So now we've written this as sum of three terms, the linearity of the Laplace transform, which comes from the linearity of intervals. You can just can't take each term separately and factor out a constant, so that makes it easy to integrate these terms. Let's see, we have a couple of terms with s minus 2 in the denominator, so we combine those 3/2, that's 6/4 plus 9/4 is 15/4. A couple of s plus 2's, so we combine those. 6/4 minus 1/4 is 5/4. And now this is easy to take the inverse transform. This is just s minus 1 over s minus 0, so the inverse transform is e to the 0t times minus 3, e to minus 3 times 1. 1 over s minus 2, the inverse transform is e to the 2t, and we got the 15/4 out front. And this is s minus a minus 2. So there's your solution. And you'll always be able to get to the point where you can say Laplace transform y equals something, and sometimes very difficult to actually find y. But you use that table and you try to get things into the form of the table using it backwards. And again, Laplace transform actually gives us the solution that satisfies these initial conditions. If you want the general solution for some reason, you just say y of 0 is a, y prime of b or 0 is b, and go through the same process, and you'll get a and b in the solution. And that's a form of the general solution that's particularly nice, because if you want to plug in the initial conditions later, you do it really easily. Okay, our last example is another second order equation with initial conditions y of 0 and y prime of 0. By the way, if your initial conditions are at something other than 0, like 5, then you probably want to just make a change of variable, and capital T equals little t minus 5, and so it is. So your initial conditions are at 0, because the Laplace transform formulas are all assuming the initial conditions are at 0. So make a change of variable, then when you get through, change it back. But usually the initial conditions are at 0. So take the Laplace transform on both sides. The right-hand side, the Laplace transform, you normally just look it up in the table, but this one's 0, so that's easy. And Laplace transform y double prime minus 2 Laplace transform y prime plus 10 Laplace transform y. Use the usual formula for y. L of y double prime, it's s squared Laplace transform y minus s y of 0 minus y prime of 0. Then minus 2 Laplace transform of y is s Laplace transform of y minus y of 0. 10 Laplace transform of y. Get the Laplace transform of y together. You got s squared minus 2s plus 10. And then take the other terms on the other side. You have s y of 0, y prime of 0, and here you have a plus 2y of 0, so it goes on the other side as minus 2y of 0. Now plug in y of 0 is 1, y prime of 0 is minus 5, so that's just s minus 2, and then minus 5. So you have s minus 7, and you divide by s squared minus 2s plus 10. Now at this point, if you could factor s squared minus 2s plus 10, you should do that. Even if it if it has real roots, you can factor it, even if it's not a nice integer. If the roots are involve square roots, that's a mess, but it's okay. You still factor it and use partial fractions. But in this case, this one doesn't factor. The roots are complex, so you can't factor it. If you could, you'd use partial fractions. If you can't factor it, what do? Well, you complete the square. See, s squared minus 2s. If you had a plus 1 here, that would just be s minus 1 squared. Well, you got a 10, which is a 1 plus a 9. So break the 10 up into 1 plus 9, and you have s minus 1 squared plus 9, which is 3 squared. So you've got by completing the square, and by the way, if you can complete the square, that means you couldn't have factored it. And if you could factor it, you couldn't complete the square, because completing the square means both terms are positive, so it doesn't have a root. So either complete the square if you can't factor it, and factor it if you can, like in the last example. This example you can't. So you complete the square, s minus 1 squared plus 3 squared. And now how does that help us? Well, let's look at the Laplace transform table. So you use this sort of like an integral table. You look for something on the right here that's close to what you have. And we see two of them here. This is a constant over s minus a squared plus omega squared. And here's s minus a over s minus a squared plus omega squared. The denominator is, we've got exactly this denominator. It's more important to get the denominator looking like what it is here, because the numerator you can break it up, the denominator you can't. So we've got two formulas here that might be useful, because we have s minus 1 squared plus 3 squared. So we've got the denominator with a equal to 1 and omega equal to 3. So we either need a 3 or an s minus 1 in the numerator. Well, we've got an s minus 7, so we don't have s minus 1 or a 3. But the numerator, we can break it up. Denominator, you can't. So, a has to be 1 and omega has to be 3. So we would need an s minus 1, but we got an s minus 7. Well, we can break that up as s minus 1 minus 6. And now we've got s minus a over s minus a squared plus 3 squared. That was one of the formulas. That was the e to the at cosine of omega t. And the other one, we got a minus 6. Well, we need an omega, which is 3, but that's no problem. We can break the minus 6, factor out a minus 2, and leaves a 3 there. So now we've got a minus 2, and then we got a omega over s minus a squared plus omega squared and s minus a. So this is exactly of the form, the Laplace transform of e to the 1t cosine of 3t, and this, without the minus 2, is exactly the form of e to the 1t sine of 3t. So there's the final answer. So far we can't solve anything that we didn't already know how to solve in earlier chapters. Left-hand side has to be linear constant coefficient. The right-hand side, well, we know how to solve it. The right-hand side is a sine or cosine or exponential or a polynomial. But with the Laplace transforms, you can solve it for more general right-hand sides. This is a very incomplete formula. There are more complete formulas of Laplace transforms that have other functions. But in particular, in the next video, we're going to see how to handle discontinuous functions. This u sub a is a function that's 0 up until a and then suddenly becomes 1. And we'll also see how to handle the right-hand side being a delta function, which is essentially infinite at one point and 0 everywhere else. So we will be able to solve some problems that we couldn't solve before using Laplace transform.